Hi, my name is Ilan Shifter, and this is an introduction to SPDX version 3. SPDX is a popular SBOM format. SBOM stands for Software Bill of Materials. There's another popular format called CycloneDX, but they take very different approaches. CycloneDX has a tree-like structure. It is easier to learn and to work with. SPDX has a graph structure, which makes it much more flexible and scalable, but also harder to understand. In this video, I will go over the core concepts of SPDX. To help explain it, I will use the visual editing tool that I've created called Dots. I created it to help newcomers get started with SPDX, but it's a very powerful tool that can be used by experts to edit and explore existing SBOMs. I will leave links to the repository and the website in the video description. Let's take a look at a simple example. We start at the SPDX document node. This node is used for describing a document, not the SBOM itself. It also allows us to reference this document from other documents. An SPDX document may include multiple SBOMs, but in this example we only have one, which is usually the case. This SBOM implements the core and software profiles. Profiles are new in SPDX version 3, and they serve two purposes. First, they separate items by use case, and secondly, they allow to define conformance criteria for implementing each of these profiles. The root element of this SBOM is a package called Acme application, which was supplied by the Acme company. It depends on the latest version of Alpine, which was supplied by the Alpine Linux organization and contains the OpenSSL package. The Acme application contains the npm elliptic package, which was supplied by this guy, and here's the link to the repo. And it was made available by Jane Doe. We have no clue who she is, but at least we've got her email. Great. Now, Jane created a creation info node together with the Acme company, and this node includes the SPDX version and the creation date. It's important to note that every SPDX element is required to have a creation info. In this example, there's only one creation info node, which all elements connect to, but this is not required. You may be wondering why we're not seeing the edges connected between the elements and the creation info. That's because Dots hides them to remove clutter from the canvas. If you want to know which elements are connected to a creation info, just click on it. And as you've seen throughout this journey, selecting a node would highlight its direct connections and dim everything else. Before we continue, here are some tips and tricks about using dots. To get information about an edge, just double-click on it. To learn about a field inside the node, click on the question mark. And for information about a node, click on Get Info. Here's the node's ID, and here's a snippet of its serialized version in a JSON LD format. To delete a node, click here or hit backspace. And finally, we can save our SBOM to a file, which would also save the location of each node on the canvas. So the next time we load it, the nodes will appear in the same locations. Let's clear our canvas and re-import this SBOM. We can do this by either selecting it or by dragging it to the canvas. The SBOM is imported in a collapse mode. We can expand it and collapse it, or do the same by double-clicking on it. We can move it around, and all its collapsed nodes move with it. And by the way, we can do this with any node in the SBOM. So if, for example, the Acme application seems a better representation of our SBOM, we may use it instead. Collapsing SBOMs is especially helpful when working with multiple documents on the same canvas. Of course, real SBOMs are much larger and more complicated. They may include data that arise from different sources at different times, or even reference data outside the SBOM, and that data may or may not exist. I know it sounds weird, but referencing data that should exist somewhere is a very common use case. Maybe you know it's there, but you don't have access to it. Or maybe you prefer not to disclose it to everyone. In any case, it's better to reference the data than to ignore it. To handle such complexity, SPDX uses the RDF standard to store information as a graph. It uses RDFS and OWL to model its specifications, and SHACL to enforce constraints. Now, if you've never heard these terms before, that's okay. I call these technologies the future of the past, because they once were the enablers of a future that never arrived, the semantic web. But it wasn't their fault, and they're very powerful and used in many domains. And they've got superpowers when it comes to describing huge graphs with complex relationships and missing data, which is very common when describing supply chains. The next part of the video is much more technical. I'm going to go into details about RDF and how it's used by SPDX. There's a lot to cover, but I promise to make it as simple as possible. So buckle up, let's go. RDF uses a simple method for constructing graphs from a list of statements, also called triples. Here is a triple. 1, 2, 3. Node, edge, node. In RDF, these are called subject, predicate, object. And here's another triple, subject, predicate, object. The difference is that in the first statement, the object is a node. In the second one, it's a value, also called the literal. And this is important to understand, because everything in RDF is described using IDs, except for literals, which are just values. For example, let's add a new agent to our canvas. If this agent happens to have the same ID as this agent, they would be merged. That's because IDs in RDF are unique. This is how chains are created. Here's another example. If both of these agents have the same ID, then they must be the same agent. This is how junctions are created. So you can see how this simple idea of using a list of triples to construct chains and junctions can allow us to construct any graph that we want. Cool. But if RDF IDs are unique, how come we have two package nodes? That's because package is not the ID of the node. Here is the ID of the node. And this triple is made of the ID of this node, the ID of this edge, and the ID of this node. Or in the case of a literal, it is made of the ID of this node, the ID of this edge, and this value. So if we add another package and give it the same name, these nodes won't be merged. That's because RDF values are just values and don't need to be unique. When I started working with RDF, I found this concept very confusing. I got how it works, but I didn't get why it matters. But this is a very important concept, and I hope I made it clear for you. Let's continue. If this node is described using its ID, then what is package? Package is a class, and like in object-oriented programming, classes are instantiated and may inherit from other classes. The concept of classes and properties is not part of the RDF standard. It was introduced in an extension called RDFS, RDF Schema. And there's another extension called OWL which add additional capabilities. But for the sake of simplicity, I will use just RDF for everything. Here's the definition of the package class. And here is the ID of this class. If we try to follow this URL, we get nowhere. And nowhere is not a place. So why does it look like a URL? Or even more confusing, a secure URL? Well, that's a vestige from the semantic web era, which never happened, but its conventions prevailed. This kind of ID is called a URI, which stands for Uniform Resource Identifier. And there's also IRI, which allows for internationalized characters. In SPDX, IRIs are made of 3 parts. This is the prefix to all SPDX classes and properties. This is the profile name. And this is the class name. So to instantiate a node as a package, we add another triple that says the ID of this node is an instance of the ID of this class. If we go back to the package description, we can see that it inherits from the software artifact class, which inherits from the artifact class, which inherits from the element class. And that's it, because the element class is the base class for all SPDX elements. And I'll just note that the ID of the element class is called SPDX ID. And this is a good time to remind you to fasten your seatbelt, because class properties in RDF are nothing like class members in object-oriented programming. So if you're a software developer, the next part would require some brain stretching. In RDF, properties are used for instantiating edges between nodes. Property definitions may include source classes and target classes. In RDF, the source is called domain and the target is a range. For example, we may connect a package to an agent using an originated by property, but not the other way around, because the originated by property is defined as going from package to agent, but not from agent to package. To illustrate this concept and emphasize its importance, let's see how this tool works. When dot starts, its class menu is empty. It then fetches and parses the SPDX ontology. An ontology is just an RDF document that contains all the class and property definitions, and SPDX uses it to model its specifications. Dots uses this ontology to construct the class menu and to group classes by profiles. When dragging a class from the sidebar to the canvas, it instantiates the class and generates 2 menus. The first menu includes data type properties, which can be used for assigning values to the node. And because package inherit from software artifact, the software artifact properties are also included in this menu. Same goes for artifact and element. The second menu is for object properties, which may be used for connecting nodes to nodes. If we drag a property to an empty spot, dots generates a new instance of the target class. If it finds existing instances, it highlights them on the canvas, so we may connect to them instead. And like we've seen with the data types, this menu also includes the inherited properties. And finally we get to the example I wanted to demonstrate. If we drag a person to the canvas, we may connect a package to it using the originated by property. But this property has artifact as source and agent as target. The reason we can still do this is that package is a subclass of artifact and person is a subclass of agent. And that's how RDF inheritance works. Here's another example. In this case, we try to draw a verified using edge from a package to a new instance of integrity method. But dots doesn't allow it. Could this be a bug? Nah, I don't do bugs. And luckily for me, this is indeed a feature. Dots doesn't generate an instance because integrity method is defined as an abstract class, and dots uses a white background to indicate it. An abstract class is an SPDX concept, which means that a class shouldn't be instantiated directly. To avoid confusion, abstract classes are also hidden from the class menu. But of course we may instantiate their subclasses. For example, we may instantiate a hash and draw a verified using edge from package. This works because package is a subclass of element, and hash is a subclass of integrity method. And I'll just mention that properties, just like classes, may inherit from other properties. But SPDX doesn't use this capability, so let's move on. Sometimes there's a need to impose additional constraints. And for that, SPDX uses another extension called SHACL. Dots uses the SHACL definitions, called SHACL shapes, to help us create valid SBOMs. For example, the package version property has a maximum cardinality of 1, which means that the package may only have a single version associated with it. If a package already has a version, dots won't allow us to add another one. On the other hand, if a property has a minimum cardinality of 1, dots would add it to the node on instance creation, and it won't allow us to remove it afterwards. Based on the SHACL definitions, dots can also figure out which value types to expect. For example, SHACL requires the value of the build time property to be a timestamp. Dot uses this information to indicate the data type in the menu and then validates the value. And in this case, it also provides us with a date picker. SHACL can also be used for enforcing string constraints. For example, the spec version of the creation info node has to match a semver pattern, and dots warns us if it doesn't. Another example is the algorithm property of a hash, which needs to match a string from a vocabulary of strings. In SPDX, there are multiple vocabularies, so this is very helpful. Nodes with invalid values are marked with a red badge, and if it's missing an object property, dots places red badges along the menu path. For example, this package is missing a creation info property. We add the missing edge, and the badge disappears. And by the way, if we try to save an SBOM with a missing object or invalid value, dots would warn us and point us to where the issue exists. Sometimes we may need to reference the same data from different nodes. For example, the creation info node from the SBOM example we saw at the beginning of the video was referenced by multiple nodes. But this is not a regular node. It's a blank node. Blank nodes are just like regular nodes, but instead of a globally unique ID, their IDs are unique only within the graph. So unlike regular nodes, which may be referenced from other graphs too, blank nodes may only be referenced from nodes in the same graph. And it's worth noting that the ID of a blank node always starts with an underscore, and may change every time it's loaded into the canvas, which is totally fine as long as we update the nodes that reference it to reference its new ID. But dots handles this for us. The important takeaway is that not all SPDX classes inherit from element, and those that don't are instantiated as blank nodes, which can only be referenced from other nodes in the same SPDX document. At this point, we have everything we need in order to store information in an SPDX document. But what if we need to add information about an edge? For this, SPDX leverages a technique called enary and provides us a relationship class. For example, we can use a relationship to connect from a package to its dependencies. And we can see that a relationship is limited to a single from edge, but may have multiple tos. Another example is using a relationship to associate between a vulnerability and a package. But the real benefit in using a relationship node instead of an edge is that we may add metadata about the edge. For example, we may indicate the date in which the vulnerability was associated with the package, or point to the person that associated this vulnerability. Relationships provide SPDX with a new level of flexibility and expressiveness. but unfortunately they also blow up the SBOM. This known limitation of RDF should be mitigated in RDF 1.2. But until that's out, relationships are the way to go. And that's it. I hope you enjoyed this video and also learned something new.